Yeah, hi everyone. I'm Till, as you already know, and I'm a Flink committer. These days working mainly on the machine learning library of Apache Flink. And today I'm going to tell you a little bit about how to compute recommendations at an extreme large scale with Apache Flink. As the title of my presentation indicates, I have divided my talk into 3 parts. In the first part, I'm going to talk a little bit about recommendations in general, how you do it with collaborative filtering. Then I will introduce Apache Flink for those of you who haven't heard about it. And last but not least, I will fuse these 2 things and show you how to implement a recommender system which can deal with really large rating matrices. So let's get started. First, I guess that every one of you got somehow in touch with some kind of recommender systems, because these days they are basically everywhere on the internet. So no matter whether you buy some products on Amazon, or you watch some series on Netflix, or listen to some songs on Spotify, there's some system in the background trying to analyze your preferences, and based on these preferences gives you new suggestions of what you should consume next. And well, of course, this is not done because out of charity by the companies. They want to improve the user experience and thus bond the user stronger to their product, so that eventually the sales and revenue is increased. And due to that, the whole recommender system thing is really big these days. But how does it actually work? Well, to give you a short example, let's assume we want to recommend some websites to our customers. And our customers are the king, the queen, and their daughter, the princess. And they visit the 3 websites, Amazon, Facebook, and Twitter. So what we know is, from our log data, that the king really likes to spend some time on Amazon, because there he can spend his wealth. Furthermore, he spends a good amount of his time on Facebook, where he keeps in touch with his fellow kings and queens, and well, can brag about his latest conquest, for example. So, and additionally, we know that the time his daughter, the princess, spends on Amazon is also not too little, because apparently the pocket money is not too bad either. So from the shared preference of the king for Amazon and the preference of the princess for Amazon, we can deduce that maybe the princess would also like to spend some time on Facebook, because the king has the same preference. And so we could simply recommend Facebook to her. That's basically how collaborative filtering works. The idea, so to say a little bit more abstractly, is if you want to recommend items for user A, what you do is you look for users who have shown in the past a similar consumption behavior. And based on what these group of people have consumed, you can then make recommendations to this user A. And well, how do you find out whether some users share a similar preference for some kind of products? Well, here's where the latent factor models come into play, which basically assign to each user a set of preferences, and to each item a set of characteristics which somehow describes the product. And usually what is done is that these kind of features are like represented as numerical vectors, such that the scalar product of these vectors gives you a preference value for a user and an item. So the higher this value is, the more likely it is that the user likes this item. Before I get to the point where I tell you how to calculate these latent factors, let's get one step back and consider what we have initially as input. What we have is user item ratings. These can either be explicit or implicit. Explicit ratings means that, for example, the user, after you've watched a series on Netflix, gives 1 to 5 stars to it. That's explicit weighting. An example for implicit weighting would be that you analyze the behavior of the user. For example, you measure how long he stays on a website or how often he watches a certain film to get a kind of weighting value for it. And these weighting values can be organized in a matrix where the rows are the users and the columns are the items. And of course, this matrix is by no means dense. So it contains a lot of blanks because not every user has seen all movies or listened to all songs. So the goal is now to fill in these blanks. And that's what we going to try to do next. Please bear with me on this slide. That's going to be one of 2 slides with formulas, but it's actually really easy. So what we have is we have a weighting matrix. And to find the latent factors, we have to find 2 matrices, the user matrix X and the item matrix Y, such that the product of these 2 matrices gives you approximately the weighting matrix. Once we found these 2 matrices, which are usually of low rank, we also have found our latent factors, because the rows of the user matrix X are the latent factors of the users, and the columns of the item matrix are the latent factors of the items. So, but how can we find these 2 matrices, X and Y? Well, here, that's a case for machine learning, where we can apply some methods. But in order to apply some machine learning methods, we usually need some kind of loss function which tells us whether our solution we found is a good solution. And in our case, we use the root mean squared error, which might sound like complicated, but actually it's only the sum of the sum of the squared differences of the prediction values and the weighting values. So the smaller the sum gets, the more closely, the better is our approximation of the weighting matrix. So yeah, that's it, basically. Now, since we have like a loss function, we can apply an optimization algorithm, which will find us our X and Y values. Well, the problem here is that the loss function depends on 2 variables. That's the item matrix X, Y, and the user matrix X. What we could use, for example, is stochastic gradient descent. This always works. But today I want to show you a different approach, which is called alternating least squares. The idea of alternating least squares is that, that by fixing one of the variables, let's say the item matrix Y, we obtain a quadratic optimization problem. And we know that's easy to solve. We only have to take the first derivative, set to 0, and solve for the unknown. I bear the math here, I spare the math here, and you have to trust me that this is right. If you do that, or do some reformulation of the equation, you end up with this update formula for user vector xu. What is interesting to see here is what we actually need to compute an updated user vector. And that is actually all the ratings the user has done, so the rating values, and only those item vectors for which the user has given a rating. That's going to be important later on. OK, now we've seen how we can update the user vectors with respect to the item vectors, so if it's fixed. So how can we finally end up with an overall solution of our optimization problem? So that's quite simple. We first fix the item matrix Y, update the user matrix X, and use this value in the next half step to update the item matrix Y. And these 2 half steps gives you what we call like an ALS iteration step. So we executing these 2 steps repeatedly improves incrementally your item and user matrix X and Y. And if you do that until you converge, you have solved your optimization problem. And that's how you factorize, or can factorize, matrices. OK. In the beginning, I said that we want to do recommendations at an extreme large scale. So this means we're talking about data sizes which no longer fit in the memory of a single machine. So what we have to do to make it still feasible is to implement a distributed alternating least squares algorithm. And that's where Apache Flink comes into play. For those of you who have never heard about Apache Flink, I will give you a short introduction. Apache Flink is a parallel stream processing engine. And as such a system, the key component of it is a streaming data flow runtime. The streaming data flow runtime allows you to, or enables you to execute data flow programs in parallel. And the data flow can be either a batch job or a streaming job, actually. And it's executed on the same runtime. In order to define these data flows, Apache Flink offers you one API for batch programs, the dataset API, which is available for Java, Scala, and Python, as well as a data stream API, which is available for Java and Scala. But here is actually noteworthy that batch processing is actually a special case of stream processing. When you do batch processing, you can think of having a finite stream, for example. And there are some special code path in Apache Flink which makes the batch execution more efficient, or to speed it up. On top of the batch processing API, by now, well, one could say a rich ecosystem has been developed. So there are some extension libraries. Some of them already part of the current release. Some of them will be part of the upcoming 0.9 release, which will hopefully be released in 1 to 2 weeks. And some of them, or the most important additions, are the Hadoop compatibility layer, which allows you to run Hadoop jobs on Apache Flink. Then we have a library for graph processing, which is called Jelly. Then recently we started working on the machine learning library, where I currently spend most of my time. And we added what we call a table API, which is a really nice SQL-like declarative programming interface. So if you know SQL, then you quickly will be familiar with the table API as well. And it's really nice to work with that, actually. And the table API is also available for the streaming part of Apache Flink. But since the streaming part is younger than the batch part, the ecosystem isn't as rich yet as for the batch part. And besides these libraries and extensions, Flink is also used by many other projects as a backend, so execution backend. So, for example, it can be used by Google Dataflow API as a backend. MQL is executed on Flink. We are currently working on bringing cascading support, so that cascading jobs can be run on Apache Flink. And the Flink was added as a stream processing engine to the Apache Samora project. The Samora project is, it deals with streaming machine learning. So in that sense, Samora brings streaming machine learning to Apache Flink as well. So that is really cool, actually. And all that can either be run locally on your machine. You can start a standalone cluster somewhere on some computers and run your jobs. You can deploy Flink on Yarn. That's really easy to run some jobs. Your jobs can be executed on TAS or embeddedly. On the next slides, I will mainly concentrate on highlighting the reasons why Flink is a good fit for implementing these kind of recommender systems. But if you want to learn more about the internals of Flink, about the individual components, then I can highly recommend you the Apache Flink deep dive talk, which will be given by Stefan Even tomorrow, I think from 12:20 to 1 o'clock on stage 3. So if you have time, you should definitely check it out. It's going to be a good talk. OK, why shall we use Flink for ALS? Well, to make a long story short, there are four main points. One of them is that it has a really expressive API. It has a pipeline stream processor. It offers closed-loop iterations, and its operations are executed on managed memory. So I will explain all of these points in a second in more detail. So let's start with the expressive API. Well, the recommender is implemented as a batch job, so we have to talk about the batch API. The key abstraction of the batch API is what we call a dataset. The dataset is represents some data which is possibly distributed in a cluster. And you define your computations by applying transformations to this dataset, which generates a new dataset on which you can apply new sets of computations. And that way you specify more or less the data flow, which encapsulates your program logic. Well, since all theory is gray, let's take a look at an example, which is like the hello world of big data, the word count. Well, the goal is we have a text, and we want to count how often each word appears in this text. How can we do that? Well, first of all, we have to define some case class, which basically only stores for each word how often we have seen it. So there's a string and an int field. Then we have to read in our data, which is done in the second line. The text is represented as a data set of strings, whereas each element of the data set is one line of the text. So what we have to do in order to calculate the number of words, how often a word appears in this text, we first have to split each line into its words. And this is done by the first line with this flat map operation, where you take a line, then call split on it, and pack it or wrap it in a word instant of this case class. Next, we have to collect all these word instances, so all identical words, so that we can count how often they appear. That's done by group by, and the following sum function, which simply counts how often the word appears. And that's all to obtain the word counts. So this example should show how easy it is to program with Apache Flink, and in fact, it's a lot of fun to do, and made the development of this recommender system really easy. Next, I said we have the pipeline stream processor. Well, unlike many other data flow systems, which execute the data flow stage-wise, so one operator after another, Flink tries to bring as many operators online as possible. By doing this, we can avoid to materialize intermediate results, so that so we can simply take one element of the input, give it to one operator, take the result, give it to the next, so to pipe it through the data flow more or less. And for jobs where some of the intermediate results are so blown up that you have to write your data or the intermediate result to disk, or that even your system crashes, there it helps that we have this pipelining execution mode, because Flink doesn't have to materialize the intermediate data. Next, I've talked about closed-loop iterations. Well, many systems offer you an ad hoc iteration mechanism, in that sense that the client somehow resubmits parts of your job repeatedly. Unlike these systems, Flink offers a real iteration operator, which is part of the data flow, and which allows the optimizer to optimize programs which contain iterations. This is important for cases where you include some computations in your iterations which are actually static, so which only have to be computed once. So Flink can, or the optimizer Flink can detect these kinds of computations, pulls it out of the iteration, computes it once and caches it on the node, and so makes it available for the actual iteration. So you basically save some computations. How the iterations are specified within Flink is that you give a step function to it, which is a part of a data flow, which basically calculates from an input data set the result of the next iteration. And what happens at the runtime is that this step function is first called, or this data flow part is first called with the initial input, which generates the result of the first iteration. And this result is given back to the step function, which then computes the result of the second iteration. And this goes on until either the maximum number of iterations is reached or some kind of convergence criterion has been reached. So last but not least, I've said that Flink's operations work on managed memory. What does this mean? Well, to understand that, I want to give you some feedback or some background information on how the JVM works. Whenever you create some objects in a Java program, they're usually stored on the heap. And for these objects, it's really hard to estimate the size of these objects. So this means it is hard to detect when your heap actually gets full and when you would have to take some of the elements from the heap, put them somewhere on disk, and make new space available for new elements. This is often the case for these kinds of systems because you usually work on data which is larger than the total amount of memory you have. Flink circumvents this problem by working internally mostly on serialized data. And additionally, it comes with its own C-like memory manager. So what happens whenever an element is given to Flink, that it is serialized. So it's given to Flink's serializer framework, which serializes the objects into some buffers of the managed memory. And this memory is managed by the memory manager. And the manager notices when there are no more buffers, free buffers left. This tells them that some of the buffers which are full have to be spilled to disk, from where they can, at a later point of time of the execution, can be retrieved. And that way, Flink avoids to, Flink avoids to, or you will we can say never see an out-of-memory exception caused by one of the internal components of Flink, because it will always gracefully spill to disk if it's needed. Okay, so much for Flink. Now let's get back to the actual implementation. Okay, to understand or to see what we have to do, we have to take a look at the update formula again. So what we see, we can update the user vector XU by, well, we need the ratings of the user U and the rated item vectors of the, the item vectors which the user U rated to compute the updated value of XU. To illustrate that, let's try to do it for the first user. So we see in the rating matrix that the first user has rated the second and fourth item, right? So what we need to calculate the new x1 vector is these two ratings, as well as the item vectors, the second and the fourth item vector. When we have these informations and get them on one node, we can calculate the updated vector. So we can generate or get these information to one place by first joining the rating matrix with the item matrix, where we use the column ID as the join key, and then group these pairs on the user ID or row index of the rating matrix. That's all we have to do to get all information in one place to compute the updated value for x1. However, here in this example, we already see one of the drawbacks of this approach. That is that user 1 and user 2 are actually computed on the same node, right? Additionally, we see that user 1 and user 2 have both rated the second item. So even though they are kept on the same machine, the second item vector has to be sent twice to the same node. So we are basically sending redundant information over the network, which is bad, actually. But let's first take a look at the pros of this approach. Well, the pros of this naive implementation is that it is straightforward and thus really easy to implement and maintain. So the code is easy. However, we have a lot of network I/O with this approach because first of all, we send redundant information over the network. And secondly, since we did not pre-partition the ratings matrix, we have two shuffle steps. One after the first join operation, and a second shuffle step after for the group reduce operation. And shuffles means always like sending the data across the network, which is bad. So can't we do any better? Well, in fact, we can. We can do better by addressing these two last problems. So namely, sending redundant information and having two shuffle steps. So first of all, what we can do is we simply group all the users which are computed on one node together. So for example, for node 1, we would create a user block which contains the first and the second user. Once we have done that, we can also group all the item vectors which we need to calculate the updated values for these two users. So basically the second and fourth item vector. But here it's important to note that that all these item vectors are only sent at most once. So this drastically reduces the amount of network traffic you have. And last but not least, we can pre-partition the rating matrix once according to the user blocks and once for the item blocks, and keep them on the machines. That way, the first join operation happens completely locally and well, you don't have to do a shuffle step, which is nice. So if we sum that up, well, the pros of this approach is that we significantly could reduce the network I/O. First of all, by avoiding this duplication of data we send, and by caching the ratings, which well, gets rid of one shuffle step. However, the con is that first of all that we have to store the rating matrix twice because it's duplicated because of the different partitionings, and the code. Well, I haven't put it here. The code got more complex, well, significantly more complex. However, when we take a look at the performance results, we see that the advantages clearly outweigh the disadvantages. So what we've done here is we've run some experiments on matrix factorization on a 40-node Google Compute Engine cluster, where each of the instances was 8-core with 52 gigabytes machine. We calculated 10 ALS iterations with 50 latent factors for rating matrices of varying sizes. We started with really small matrices and slowly scaled it up. What we can see here is that the naive ALS implementation performed worse than the blocked ALS implementation. That's not so surprising. And at some point, there was, I think, 8 billion, where the rating matrix had 8 billion non-zero entries. For matrices bigger than that, it took so long that, well, the calculation didn't finish. So in contrast to that, we see that the blocked ALS implementation scales much, much better. And we could factorize matrices with up to 28 billion non-zero entries, which is on the scale of Netflix and Spotify. So that is a real-world problem, actually. It took us 14 hours to finish the 10 iterations. And by doubling the number of cores and the memory we have, we could even cut the time down to 5.5 hours, which now allows to calculate the matrix factorization multiple times a day, which allows you to do well, more like up-to-date recommendations. OK, now you might say, well, this is quite nice, but if I have to implement it myself, then maybe it's not worth the effort. However, you don't have to worry. The ALS implementation is part of the machine learning library, so it's really easy to use. And that's what you can see on the right side, how you would use it. First of all, you would have to instantiate the ALS factorizer object, read in the weighting matrix, which is represented as a data set of tuples, row index, column index, weighting value. Then you specify some parameters for ALS, namely the number of iterations, how many latent factors you want to have, and the lambda value, which is important for the regularization. The actual factorization happens in the fit method, where you provide the rating matrix and the parameters. And once you've done that, you can basically query or calculate for row or user ID, item ID pairs the predictions by simply calling ALS predict, or where you provide the pairs for which you want to calculate the predictions. But that's not all. You can do with the current machine learning library. There are also algorithms included for clustering, regression, and classification tasks. And all comes with a scikit-learn-like pipeline mechanism. So it's really easy to set up even complex analytical pipelines. Yeah, this brings me to the conclusion of my talk. So what have you seen today? Well, first of all, you've seen how one can make recommendations using collaborative filtering. You've even seen some math. Then you've seen Apache Flink. That Apache Flink is a powerful parallel stream processing engine with which you can implement an efficient matrix factorization system, which scales up to really, really large matrix sizes. Yeah. The last thing maybe which is left for me to do now is to draw your attention to the upcoming Flink Forward conference. This will take place on the 12th and 13th of October. So if you got interested or maybe even want to give a talk there, then save the date. If you can't wait that long, you should go to flink.apache.org and check out Flink or follow Flink on Twitter at Apache Flink. And yes, with that, I'd like to thank you for your attention, and I hope you have enjoyed the talk. Thank you very much.